Right, quantum mechanics. Quantum mechanic. All right. So, Bohr. Okay, remember Rutherford. Rutherford had the gold foil experiment. He's the one who proved that the nucleus exists. That's where you find all the protons, incredibly small, incredibly dense. Suggested the existence of the neutron. Well, the problem with that is that atoms can't exist. You see, if you have an accelerating charge, it will give off radiation. So, say you have, an electron and you accelerate it, then it will give off electromagnetic radiation. Acceleration means a change in speed or direction. So if you have an electron going in a circle, it will constantly be accelerating because it's constantly changing direction. Therefore, it should constantly be giving off electromagnetic radiation, meaning that it's constantly losing energy, meaning that the electron should spiral into the nucleus. So, according to classical physics, Rutherford's atom was impossible. It couldn't possibly exist to have electrons sort of orbiting around the nucleus. It should spiral in and just stop being an atom. So there has to be something else going on. And with that, we get the Bohr model, named for Niels Bohr, a Danish physicist. So he took information from Einstein and Planck, blackbody radiation and the photoelectric effect, and he decided to answer the Rydberg question. Why does hydrogen care about integers? It's because of quantum. So, what is quantum? Quantum literally means a unit, a thingy, an item, a single bit. Okay, the plural is quanta. Okay, it's where we get to count, contar in Spanish. So something is quantized if it's something that can only exist in quanta, discrete packets. That is to say, it's not continuous. So quantum mechanics is the new branch of science based on studying quantized phenomena. Now, quantization shouldn't be unfamiliar. Atoms are quanta. Okay, that's quantum bits of matter. Remember, the ancients argued over whether or not atom was continuous, aka infinitely divisible, or if it came in discrete chunks of matter. We now know that it does come in discrete chunks of matter, atoms and then subatomic particles and so on. Well, other things are also quantized. Light is quantized. It comes in individual bits of light called photons. Other things, other forms of energy, ways of storing energy are also quantized. Oops. All right. So, in the Bohr model, hydrogen cares about integers because that's where electrons can exist, only on specific energy levels. The first energy level, the second energy level, the third energy level, and so on. Those energy levels are quantized. That energy is quantized. And likewise, photons of light are quantized. So only light with the correct amount of energy, aka the correct frequency, the correct color, can interact with an electron and move it from a lower energy level to a higher energy level. Okay, that would be an absorption spectrum. And when an electron falls from a higher energy level to a lower energy level, it will release that specific amount of energy. And that amount of energy will determine the frequency or color of the light released. And that's what gives us the emissions spectra. So that is why that's why hydrogen cares about integers, because those integers represent the energy levels where electrons exist. Okay? And there's a certain amount of energy separating the first and the second energy level, a certain amount of energy separating the second and third, and so on. And that's where you get the colors of light for the different spectra. So, the pros and cons of Bohr's model. Let me go ahead and... no questions yet. Pros, it's a handy explanation. It fits neatly with the new quantum stuff that was popular at the time, and it matches with the observations. Cons. Why does an electron only have specific energy levels? It's an unthinking, minuscule chunk of matter. It kind of shifts the problem back by a level. Why does hydrogen care about integers? Well, because electrons can only exist at certain energy levels. Why does an electron only have specific energy levels? Shut up. Okay, so we have to keep going. And that's where we get Louis Victor Pierre Raymond de Broglie, the 7e Duc de Broglie. You don't have to remember his full name. We always just call him de Broglie. So de Broglie said, dude, so like light is a wave that does particle shit, right? So why can't an electron like do this wave thing? And physicists were like, dude, that's so deep. So what he was saying was, if light is both a wave and a particle, why can't electron be both a particle and a wave? So, a little bit of math. Planck said that, energy is equal to h nu, or hc over lambda. That is to say, light comes in individual packets of energy called photons, and the amount of energy is based on frequency or wavelength, whichever you want to call it. Now, Einstein, with his relativity, said that E equals mc squared, that matter is condensed energy. So de Broglie said, boom, put those two together. Hc over lambda is equal to mc squared. You rearrange that, you combine it, and you get the de Broglie equation. Lambda is equal to h over mc, or, since these things are traveling at actual velocities and not at the speed of light, lambda is equal to h over mv. The wavelength of a particle, lambda, is determined by its velocity, v. Or, if you're physicists love using momentum. Momentum is mass times velocity, so h over p. P meaning momentum. So let's go ahead and apply that to the electron. An electron has a mass of 9.11 times 10 to the negative 31st kilograms. And the speed of an electron in a hydrogen atom is 2.2 times 10 to the 6th meters per second. So we go ahead and we plug those numbers in to the de Broglie equation. Lambda equals h over mv. H, Planck's constant, 6.626 times 10 to the negative 34th joules seconds. And then we have the mass of the electron, 9.11 times 10 to the negative 31st kilograms, and the speed of the electron, 2.2 times 10 to the 6th meters per second. Just a quick note on units. The reason the de Broglie equation works here, the joule, 1 joule, is equal to 1 kilogram meter per second squared. Or sorry, meters squared per second squared. Yeah, that's kind of ridiculous, but it works. This is when you break the joule down into its basic unit of energies, you get kilograms meters squared per second squared. All right. So then you have the joule second. The joule second divided by kilograms times meters per second, meaning that you have kilograms meters squared per second squared times seconds divided by kilogram times meters per second. Whew, that's a lot of units floating around, but kilograms cancel out, one of the meters cancels out, this cancels out one of the seconds, and this seconds cancels out the other one, leaving you with meters all by itself. So that is how the units for the de Broglie equation break down to wavelength in meters. So you plug in the numbers that we had for the electron, and what you get is 3.3 times 10 to the negative 10th meters, or 0.33 nanometers, or 3.3 angstroms. Okay, so first off, notice that we're looking at about the same scale as a photon. Photons are going to be, somewhere in the nanometer or hundreds of nanometers region when it comes to their wavelengths. So, this is about what we should expect. The angstrom, or 10 to the negative 10th meters, it's a common unit of measurement in, well, not common, but it shows up occasionally in chemistry because that's about the scale you get for atomic radii and for chemical bonds. Chemical bonds are often about 1 angstrom long. So we should expect the wavelength of the electron to be on the scale of the angstrom. This all makes sense. The wavelength of the electron is somewhere around what we're looking for with the size of the atom. Okay, so this is all starting to make a little bit of sense. This is all starting to look like it might be a real thing. So, is de Broglie useful? Well, it explains why Bohr's model works. If electrons have wavelengths, then they can only exist at a certain wavelengths if you get constructive interference. Remember, interference is when peaks line up with peaks and troughs line up with troughs. So at a certain radius, a certain distance from the nucleus, the electron's wavelengths will line up perfectly with itself. Okay? Peak of the electron will line up with the peak of the electron. The trough of the electron will line up with the trough of the electron. So here you have n equals 3, where you have a perfect multiple of the wavelengths, and here you have n equals 4, where you have a perfect multiple. In between those two wavelengths, the electron can't exist because you don't get constructive interference. You get destructive interference. It doesn't work. It cancels out. Peaks line up with troughs. Troughs line up with peaks. Okay, so at the very least, this is a very tempting sort of model. But is it true? Well, to figure that out, we would do the double slit experiment. We have a barrier with two narrow gaps in it, and then we have a wall behind it where we can see where the electrons land. We fire electrons here, and we see where they land on this barrier. If they act just like particles, it would be like firing bullets out of a gun, and we would just get two places where electrons hit the wall. But if electrons have wavelengths, then we should see constructive and destructive interference, and we should get this interference pattern. And that is exactly what we see. We get an interference pattern from electrons. Electrons do have wavelengths. So this is a very handy experimental confirmation of de Broglie's hypothesis, meaning that he had ushered in the full wave-particle duality of quantum mechanics. So in classical physics, waves and particles are totally separate things. Matter is made of particles. Energy travels in waves, and they're just not at all related to each other. But in quantum mechanics, they are at the same thing. At the smallest scale, waves are particles, and particles are waves. Now, in the everyday world, the stuff you and I interact with, classical physics still works, and the wavelengths of objects don't matter. Okay, we're just too big. It just doesn't work. But down at the very tiniest level, it does work. Wavelengths still do exist. They still do matter. All right. So, oh dear, I didn't put these in. So I will pop out real quick and see if I can find handouts. Nope, that's not the one I want. Lectures? Did I put it? Yes, I did. Okay, so the QM worksheet. So these are some examples of things that they could ask you about on this here upcoming test. Using the de Broglie equation, what is the wavelength of a fastball? I went ahead and I switched the units over already. So the mass of a baseball is 141.748 grams. And the speed of a fastball, 100 miles an hour, is 44.704 meters per second. Okay. So let's go ahead, and I'm going to have to go turn the lights on real quick, because it's getting kind of dim in here. All right, so we plug those numbers for our baseball into the de Broglie equation. Okay, so de Broglie's wavelength is lambda equals h over mv. So h is 6.626 times 10 to the negative 34 joule seconds. The mass of the baseball, we have to put it in kilograms, otherwise this doesn't work, because the joule is kilogram meter squared per second squared. So we have to convert from grams to kilograms. That means it's 0.141748 kilograms times 44.704 meters per second. Okay. So those are what we plug into our calculator. All right, so 6.626 divided by 0.141748 divided by 44.704 gives us 74 times 10 to the negative 34th meters, or 4.674 times 10 to the negative 33rd meters. All right, that is a ridiculously small wavelength. Oh, wait, no. I was looking at the wrong numbers. I was looking at something else entirely. Okay, it is 1.046 times 10 to the negative 34th meters. I'm sorry. All right, so yeah, that is still, either way, a ridiculously small wavelength. The de Broglie wavelength does not matter at normal distances, normal scales, normal speeds. It's just not a thing. But let's go ahead and look at this second one. How fast would a typical adult human male, 85 kilograms, have to be moving in order to have a wavelength of 50.5 centimeters? You know, the width of a wall. Okay, so would you be able to travel through a wall? Okay, let's go ahead, bring the thing back up. Okay, so wavelength equals h over mv. So lambda v equals h over m. Speed is equal to h over m lambda. Okay. So I did that because we know our wavelength. All right. 6.626 times 10 to the negative 34th joules seconds. Our mass needs to be in kilograms. It already is. Our speed, our wavelength needs to be in meters. So times 0.505 meters. Just convert the 50.5 centimeters to meters. So that is what we plug into our calculator. So 6.626 divided by 85 divided by 0.505. And that gets us 0.15. Yep, that's where we stop. Meters, oops, nope. Times 10 to the negative 34th meters per second equals 1.5 times 10 to the negative 35th meters per second. Just so you know, that is incredibly ridiculously absolute, that you cannot possibly move that slow. Just the random motion of your atoms and molecules is faster than that. You would have to be cooled down to pretty much absolute zero to have a speed that low. You cannot move low enough to have, cannot move slowly enough, I should say, to have a wavelength of any significant speed or of any significant length. Okay. The de Broglie wavelength simply is not noticeable for real life everyday objects. You absolutely will not see it. You cannot notice it. It only works at quantum mechanical scales for incredibly, incredibly small objects like electrons. All right, so those are some basic manipulations with the de Broglie equation. Let's go ahead and continue. That is it for quantum mechanics. Let's see, I've been talking for 20 minutes. Let's just go ahead and keep on chugging along with electronic structure. All right. So, electronic structure means we'll be talking about the internal structure of the atom. Okay. So, the quantum mechanical atom. the location of electrons, how electrons are placed around the nucleus. Okay? It is not as simple as just energy levels. As we continued to study, we found that the internal structure of the atom is more complicated. If you go back to, let's see, actually, I can bring it up real quick. The emission spectrum of sodium coupled with, oops, that's not what I wanted, this is what I wanted. Here's both the emission and the absorption spectrum. Well, you see that sodium has this double line right there. That double line right there is explained by the more complex internal structure of the atom. You see double lines in mercury as well, things like that. Okay, the internal structure of the atom is not as simple and straightforward as just energy levels. Okay? In fact, there are 4 quantum numbers that describe, I should say, the location of the electron. They function as an address. Okay, so a sort of a street address. Okay, so I call it hotel atom, and it's sort of shaped like an upside down pyramid. You have N, the principal quantum number, aka the energy level. You have L, the angular momentum quantum number, that is the sublevel. M sub L, the magnetic quantum number, that is the orbital, and then M sub S, the spin quantum number. That's just spin. You don't really have to remember these fancy names. Principal, angular, momentum, magnetic, spin. No. Just remember level, sublevel, orbital, spin. Okay. So every atom has technically an infinite number of energy levels. Okay. The energy level, the actual value of the number, is any positive integer. Okay. So 1, 2, 3, 4, etc. I consider that the floor of hotel atom. So that's down here, the bottom of the pyramid, very small. As you go up, the energy levels get bigger and bigger. Okay. Then you have a sublevel. Every sublevel is composed of one or more sublevels. Okay. So there could just be the one sublevel. You know, the level might be divided into multiple sublevels, or it might just be a single sublevel. So I call that the suite. Okay, a suite of rooms. If you go to a fancy hotel, you might just get a single room, or you might get multiple rooms grouped around a common area. Okay, so every floor of hotel atoms has one or more suites of rooms. The first floor only has one suite because the first floor is small. It's an upside-down pyramid. As you go up, you get more and more suites, more and more sublevels. So the sublevel is equal to any integer, any non-negative integer, up to or less than n. Okay, so if n is equal to 1, L can only be equal to 0. Okay, it can only go up to n minus 1. If n is equal to 2, then L could be 0 or 1. If n is equal to 3, it can be 0, 1, or 2. So that's what I mean when I say that it gets bigger and bigger, because at the first level, it's only got a single sublevel. The second level, it has 2 sublevels. At the third level, it has 3 sublevels. Fourth has 4, fifth has 5, and so on. Every sublevel is composed of one or more orbitals. Now, it might just be a single orbital is the whole sublevel, or the sublevel could have multiple orbitals. So, it's called M sub L because it's based on L. So the possible values of M sub L go from negative L to positive L. Okay, so let's go ahead and bring up paper. For n equals 1, L can only be equal to 0. M sub L can only go from negative L to positive L, meaning it can only be equal to 0. Now, if n equals 2, you could have L equals 0 or L equals 1. Now, in L equals 0, m sub L can still only be equal to 0. But for L equals 1, m sub L can go anywhere from -1 to +1. It's any one of those integers, so -1, 0, and +1. For n equals 3, L can be equal to 0, L can be equal to 1, or L can be equal to 2. M sub L can be equal to 0 when you're in L equals 0. For L equals 1, it can be -1, 0, or +1. For L equals 2, it could be -2, -1, 0, 1, or 2. Okay. So every energy level is larger than the energy level below it because it has more sublevels. And every sublevel, every suite in Hotel Atom, is made of multiple rooms, or it's made of at least one room. And the larger the suite, the more rooms it has. The higher the sublevel, the more orbitals it has. So L equals 0 only has one orbital. L equals 1 has 3 orbitals. L equals 2 has 5 orbitals. Okay, so the number of orbitals is going up in in odd numbers. So 1, 3, 5, 7, 9, 11, and so on. Okay, so level or floor in Hotel Atom, L is the sublevel or the suite in Hotel Atom, and then M sub L is the room within the suite. What about M sub S? Okay. M sub S is the spin, and it's either plus or minus 1/2. That's it. Okay. M sub L is based on L. L is based on N. M sub S is not based on any of the others. Okay. M sub S is either positive or negative 1/2. In terms of Hotel Atom, that means top or bottom bunk. The fanciest hotels have bunk beds. I don't know if you knew that. Okay, that's not true. No, they don't. They don't have bunk beds. Positive or negative 1/2. Spin is called that because electrons act as if they were spinning. Okay, that's something you hear a lot in quantum mechanics, acts as if, because the way they understand and explain things is by analogizing with real-life everyday objects. If you have an object with an electric charge, and you spin it, then it will create a magnetic field. So electrons act as if they were spinning and thus create a small magnetic field about themselves. And they can have a spin up, positive 1/2, or a spin down, negative 1/2. And don't worry about what spin up and spin down mean in physical terms. And it's positive and negative 1/2 because electrons are what are known as fermions, meaning you can only have a limited number in one space. If they were neutrons or photons, then they would have a whole number spin, an integer spin, and you could have an infinite number in one space. Okay, so photons have spin 0, and you can pack an infinite number of photons into a single location. That's what a laser beam is. Neutrons have spin 1, and they can also pack a large number into one space, and that's what the nucleus is, or a neutron star. Okay. Don't worry too much about that. Okay. Positive or negative 1/2. Positive or negative 1/2 just means you can only have a small number of electrons in one space. Specifically, you can have 2 electrons, one with spin up, one with spin down. Okay. So every floor or every level is made up of sublevels. Every sublevel is made up of orbitals. Every orbital can hold at most 2 electrons. Okay. Higher levels have more sublevels. Higher sublevels have more orbitals. Every orbital holds at most 2 electrons. It could be empty. It could have 0 electrons in it. It could be half full. It could have 1 electron in it. But at most, it can have 2 electrons. One spin up, the other one spin down. All right. Now, that's a lot of numbers. So that's why we give these sublevels letters instead. Okay? So if L equals 0, we call that the S sublevel. If L equals 1, we call that the P sublevel. If L equals 2, we call that the D sublevel. And for L equals 3, we call that the F sublevel. Okay. Once you get beyond that, we have G, H, I, J, but we never actually use those. The only way to get those is to go to really high sublevel or really high energy levels, and by the time we get there, we've run out of atoms. So we just worry about S, P, D, and F. L equals 0, 1, 2, and 3. S, P, D, F. So that means that as we go from the bottom up to the top, we have energy level 1, L equals 0, M sub L equals 0. That is the 1s orbital. And then we follow that with the 2s orbital. And then we have 3 orbitals, the second level, energy or sublevel 1. Each one of those is a 2p orbital. Okay, so 1s, 2s, 2p, another 2p, another 2p. Okay. We're in the second energy level, the p sublevel. There are 3 orbitals, and we call each of those a 2p orbital. Now, these are locations around the atom where electrons can exist. Okay. So broadly speaking, you have the first energy level where you can find an electron. Within that first energy level, you have a single sublevel where you can find electrons. And then within that sublevel, there is just the single orbital where you can find electrons. The second energy level has 2 sublevels, 0 and 1. One of them only has 1 orbital, the other one has 3 orbitals. That is to say, the first one is composed only of a single orbital. The entire thing is just the 1 orbital. The other sublevel is divided into 3 orbitals, say for a total of 4 orbitals, and therefore it can hold 8 electrons. 2, 4, 6, 8. The third level has 3 sublevels with 1, 3, and 5 orbitals total, each, I should say. So 1 plus 3 is 4, 4 plus 5 is 9. It's a total of 9 orbitals in the third sublevel, or the third energy level, so it can hold a total of 18 electrons. And they are the 3s sublevel, the 3p sublevel, the 3d sublevel. And we have a 3p orbital, a 3p orbital, a 3p orbital, a 3d 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 orbital. Woof, that is a lot. I've been talking for a while. Let me take a sip of my soda pop. Now, energy level 4 has a total of 4 sublevels, S, P, D, and F, 1, 3, 5, and 7 orbitals. So 1 plus 3 is 4, 4 plus 5 is 9, 5 plus 7 is 12, so a total of 12. Wait, is that? No. 9 plus 12 is 21. There we go, for a total of 42 electrons. No, wait. 1 plus 3 is 4, 4 plus 5 is 9, 9 plus 7 is 16. There we go. Oof, I must be getting tired. Total of 16 means we have a total 16 total orbitals in the 4th energy level. It means we have a total of 32 electrons in the 4th energy level. 5, the 5th energy level, should technically have 5 sublevels. But like I said, we never actually go beyond F in reality. We never go beyond the 3rd sublevel in reality, or sublevel 3, I should say, in reality. So really it just has 4, 0, 1, 2, 3. Again, a total of 16 orbitals for a total of 32 electrons. So when we look at Hotel Atom, when it's empty, here we have our levels, our sublevels, and our orbitals. Okay, so we have 1s, a single orbital down here. I apologize for the pop-up thing. I don't know how to get rid of that. Then the second energy level, 2s and 2p. Notice 1 orbital, then 3 orbitals. 3s, 3p, 3d, 1, 3, and 5. 4s, 4p, 4d, 4f, sp, df, sp, df, sp, df. All right. This picture shows that as you go up, the energy levels get bigger. They have more room for electrons. Every one of these blanks represents an orbital and can hold 2 electrons. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, and so on, right? Except this picture is dishonest. Sublevels have different energies as well. Okay? Every energy level is higher than the energy level below it. Every sublevel is higher than the level below that. Now, fortunately, all of the orbitals have the same energy when they're inside of a sublevel. So that is a simplification. But this picture gets a lot more complicated because 2p is higher in energy than 2s. 3d is higher than 3p, is higher than 3s. 4f is higher than 4d, is higher than 4p, is higher than 4s. And the other complication is that the energy levels get closer together as you go higher up. There is a really big gap between the first and the second energy levels. There's a smaller gap. It's still pretty big, but it's smaller between second and third. Between 3 and 4, it's even smaller. Between 4 and 5, it's smaller still. So when you look at Hotel Atom, it actually looks like this. You have 1s way down here, covered up by the thing again. Then you have 2s and 2p. So you see there's a pretty big gap between the first and the second. And then there's a tiny gap between s and p. Then you have a smaller gap between 2 and 3. And then you have, oh dear, look at that. 3d is higher in energy than 4s. 4d is higher than 5s. 4f is higher than 5p. Heck, 4f is higher than 6s. And then 5d is higher than 6s. This is a mess. Okay, yeah, that's just something you have to learn to live with. The internal structure of the atom is very complicated because once you start to get to higher energy levels, the fact that sublevels are spread out in energy and the fact that the gaps between the energy levels are getting smaller means you start to get overlap between the levels. So, if you are feeling super duper numerical, the way you know which electron goes where, you could try to memorize this chart. I really don't recommend it. But when you put electrons into the atom, they go in the bottom first. So they go into the first energy level, and then 2s, then 2p, then 3s, then 3p, then 4s, then 3d, then 4p, then 5s, then 4d, then 5p, then 6s, then 4f, then 5d, then 6p, then 7s. Okay, don't memorize this chart. Instead, we use what's known as Aufbau. That is German. It means construction or building. The Aufbau it's a number. Okay, the Aufbau number for every sublevel. An Aufbau is equal to n plus L. So for 1s, the Aufbau number is 1 because n equals 1, L equals 0. For 2s, Aufbau equals 2. For 2p, Aufbau equals 3. 2 plus 1 is 3. And then for 3s, Aufbau equals 3. For 3p, Aufbau equals 4. For 3d, 3 plus 2 is 5. Then 4s, Aufbau is 4. 4p, you can't see it at the moment, but it's equal to 5. Then for d, it's equal to 6. For f, it's equal to 7. And then 5 plus 0 is 5, 5 plus 1 is 6, 5 plus 2 is 7, 5 plus 3 is 8. Then for level 6, you have 6, 7, 8, and 9. For level 7, you have 7, 8, 9, and 10. For level 8, you have 8, 9, then 10, and 11. Okay. And the way Aufbau works is once you've calculated your Aufbau number, you fill from the lowest Aufbau to the higher Aufbaus. So you would start here at level 1. Oopsie, let's go back. You would start here at Aufbau equals 1, then Aufbau equals 2, and then Aufbau equals, oh dear, you have 2 Aufbau equal to 3. You also have 2 Aufbaus equal to 4. You have multiple Aufbaus equal to 5. In fact, you have 3 Aufbaus equal to 5, because 3 plus 2 is 5, 4 plus 1 down here covered up is 5, then 5 plus 0 is 5. Then you have multiple Aufbaus equal to 6, because 4 plus 2 is 6, 5 plus 1 is 6, 6 plus 0 is 6. 4 plus 3 is 7, 5 plus 2 is 7, 6 plus 1 is 7, 7 plus 0 is 7. Oh dear, how are you going to handle this? Well, if 2 sublevels have the same Aufbau number, then you fill the lower energy level first. Okay, so 2 plus 1 is 3, 3 plus 0 is 3. Okay, they have the same Aufbau number, but 2 is less than 3, so 2p gets filled before 3s. Likewise, 3p gets filled before 4s. But 3d gets filled after 4s because it has a higher Aufbau. And then when you want to compare 3d and 4p, they both have Aufbaus of 5. 3 plus 2 is 5. 4 plus 1 is 5. But 3 is less than 4. The energy level 3 comes before energy level 4, so 3d gets filled before 4s. Likewise, 3d gets filled before 5s. 3d gets filled before 4p. 4 plus 1 is 5. 1 means p. So 3d gets filled before 4p. They both get filled before 5s. Okay. But that is a lot. It's kind of garbage. So here is a visual representation. You draw out your levels and your sublevels. Your levels go from top to bottom in this chart. Your sublevels go from left to right. So 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f, 5s, 5p, 5d, 5f, and so on. And then you go down and left, down and left, down and left. So you start here, down and left. You've run out, you go back to the top, down and left, go back to the top, down and left, back to the top, down and left. Okay, so you start with 1s, then 2s, 2p, then 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, 4f, 5d, 6p, 7s, 5f, 6d, 7p, 7s. Whew, that's kind of complicated. Okay. This way, I think, might make it a little easier, maybe? Okay. Yes, if you're having trouble following this, don't worry. Everyone has trouble with this, okay? So we start up here, 1s. We run out, we've hit the left wall, so we come back up to the top in the second column. There's nothing here in 1p. 1p doesn't exist, but we can go down. Oh, now 2s. Now we hit the wall, we go back up to the third column. Again, there's no such thing as 1d, but there is 2p, so that comes next. Then 3s, we hit the wall, we come back up. No 1f, no 2d, but there is 3p, then 4s. We've hit the wall. We've also run out of orbitals, so we come down. No 2f, but there is a 3d, then 4b, then 5s. Then there's no 3f, but there is 4d, 5b, 6s. 4f, 5b, 6p, 7s, 5f, 6d, 7p, 8s, okay, and so on. Now, again, all orbitals in a sublevel have the same energy. But that doesn't mean the electrons can go just anywhere, okay? Electrons have negative charges. Like charges repel. So they don't want to go in the same orbital if they don't have to. So you put an electron in an empty orbital before you start pairing up electrons. Okay. So let's bring up the thing. So 1s, 2s, 2p. Say we're throwing 7 electrons in here. 1, 2, 3, 4. We represent electrons with these half arrows because they have half spin. Spin up, spin down, up pointing arrow, down pointing arrow. So that's 4, 5, 6, 7. Okay. So we don't pair up the electrons in an orbital until we have to. Okay. But now we've run out of orbitals. If we were going to put an 8th electron in here, then we pair up. Okay. Now, notice that I drew, up arrow, up arrow, up arrow when I was putting these in there. That's because unpaired electrons in the same sublevel want to have the same spin. That's a thing called degeneracy. Okay. If you're talking to an old-fashioned type, then degenerate just means probably something racist. But in chemistry, let's choose a different color, and physics, degeneracy can have slightly different meanings. Here it means that they are mostly identical. So when you have electrons with the same spin in different orbitals, then they say, we look alike. we are exactly the same, and that makes me happy. And it lowers their energy and it makes them more stable. Degeneracy can only happen if you have multiple orbitals in the same sublevel. So you don't get degeneracy in the s sublevels because an s sublevel only has one orbital. A p sublevel has 3 orbitals, so you can have degeneracy. A d sublevel has 5 orbitals, so you can have even more degeneracy. Because in the p sublevel, this guy has 2 neighbors that look like him. And a d sublevel, so if we were looking at, say, 3D, you could have 5 electrons all pointing up. So this guy looks, he sees 1, 2, 3, 4 neighbors that look like him. So the higher sublevels, not only can they have degeneracy, they can have different amounts of degeneracy. So the 3D sublevel can get really stable. The 4F sublevel, likewise, it has 7 orbitals. Therefore you can have 6 neighbors that look like you. That's a lot of degeneracy. So in the larger sublevels you get that degeneracy, and it makes a big difference. Now the other thing is that when you start pairing up electrons, you have to give them opposite spins. One will be spin up, the other one will be spin down. Okay. So that gives us another bit of vocab, the Pauli exclusion principle, named for yet another German physicist, Wolfgang Pauli. No 2 electrons can have the same 4 quantum numbers. To put it another way, if you have 2 electrons in the same orbital, they're going to have opposite spins. You can only have 2 electrons in one orbital. No more than that. And they have to have opposite spins. This is why when you try to, for example, walk through a wall, you can't. The electrons in your body are trying to occupy the same space as the electrons in the wall, and they can't. They are spin excluded, is the way we call that. They just can't occupy the same space. There's already electrons there. All right. So, oops, there we go. That is a lot, and it's complicated. Fortunately, now that I've thrown a metric ton of numbers at you, we can make it a heck of a lot more simple, because the periodic table does all of that work for you. The odd, blocky shape of the periodic table is due to orbitals. It's due to quantum mechanics. This is really, really awesome. I think this is one of the more beautiful things that we've ever discovered. The shape of the periodic table is due to the internal structure of the atom. We discovered the shape of the periodic table in the 1860s, 1870s, 1880s, and this was decades before we had any clue about quantum mechanics. This is a truly beautiful, wonderful thing. Okay. Each block of the periodic table represents a different sublevel. So over here, this narrow column on the left, that is the s sublevel. The s sublevel has a single orbital. It can only hold 2 electrons, and this block is only 2 columns wide. 1 electron, 2 electrons. Then you come over here, we have the p block. The p block has 3 orbitals, so it can hold 6 electrons, therefore 1, 2, 3, 4, 5, 6 columns. In the middle, we have the d block. The d sublevel has 5 orbitals and can hold 10 electrons, and this is 10 columns wide. And then down here we have the f block. F has 7 orbitals, and this is 14 electrons wide. Truly, truly wonderful. And thus, if you want to know what level, what sublevel you're filling, you just follow along in the periodic table. First electron goes in 1s. Second electron goes in 1s. Third electron goes in 2s. Fourth, 2s. Then the next electron goes in 2p. So does electron, 6, 7, 8, 9, and 10. All go into 2p. Then 2p is full. The 11th electron goes in 3s. The 12th electron is 3s, and now 3s is full. You come over to 3p. And then electrons 13 through 18, 13, 14, 15, 16, 17, 18 are all going to go in 3p. And then you don't even have to think about Aufbau, because what comes after 3p? Boom, 4s. So 19 and 20 go into 4s, and now you go into 3d. Notice the d block has been shifted, so 4s is followed by 3d. It's on the fourth row of the periodic table. The rows of the periodic table represent the energy levels, just as the groups, these blocks, represent the different sublevels. But 3 has been shifted because of the splitting of the sublevels, the fact that there's that overlap between the levels and sublevels. So 4s is followed by 3d. So electrons 21 through 30 go into 3d. Then 31 through 36 go into 4p. Then 5s for 37 and 38. And now 39 through 46 go into 4d. Then 47 through 54, I've lost count. I think it's 52. 46, 47, 48, 49, 50, 51, 52. Yes. Go into 5p. And then 6s for 53 and 54. And now you have to be careful because the F block technically goes right here in between 6s, 5d, and 7s and 6d. But we pulled it out, put it down at the bottom to make the periodic table fit on a single sheet of paper. So from 6s, we go down to 4f, 14 electrons into 4f, then we come back up to 5d, then over to 6p, 7s, 5f down here on the bottom, then back up to 6d, then over to 7p. Okay. So when you're putting electrons into an atom, and they will ask you to put electrons into atoms, okay, you are going to just have to follow the periodic table, and you will always have a periodic table handy. Okay. There's a periodic table in the textbook. There's ptable on ptable.com online, which I have right here. Okay, so 1s, 2s, 1s, 1s, 2s, 2p, and so on. All right. I'm going to switch back over to YouTube so that I can see if anybody has questions. All right, so as you're following the periodic table, it will tell you what level, what sublevel you're on. Okay? It'll tell you when to go on to the next thing. It'll tell you how many orbitals there are in this particular sublevel. Okay? 1, 3, 5, and 7. It tells you everything. The periodic table has all of that structure. So when you fill hotel atom, it's like just you pour electrons into a bucket, they fill it from the bottom to the top. And this gives us a couple, but, okay. From there, we have several different ways of representing electrons in an atom. We have orbital filling diagrams, we have electron configurations, and we have abbreviated electron configurations. Okay. So an orbital filling diagram is a drawing with all the electrons in their orbitals. An electron configuration is a list of all the electrons in their sublevels. Not in their orbitals, just sublevels. And the abbreviated electron configuration is a list of the electrons that matter in their sublevels. Okay. All right, so let's go through a few examples. Okay, so let's start with something small. Let's do carbon. Okay, so carbon, oops, is which element? There's P table. Okay, carbon is right here. It is the 6th element, so it has 6 electrons. So 1s, 1 electron, 2 electron. All right, now 1s is full, so 2s, 3rd and 4th. Now 2s is full. So 2p, 3 and 4, so 5 and 6. Okay. Notice that they're both pointing in the same direction. Just by habit, we typically draw unpaired electrons pointing up. There's no particular reason for that. They could just as easily be pointing down, but just the way we do it. Up is positive. We're happy people. All right. So in any event, that is the orbital filling diagram of carbon. Let's do something a little bit bigger. Let's do iron. Iron, yep, you can still see it, is element 26 here in the middle of the periodic table. It has 26 electrons. This is going to take a little bit longer. It's going to take a little bit more space. So 1s, 2 electrons. 2s, that gives us 2 more, so for 4 electrons. That's followed by 2p. 5, 6, 7, 8, 9, 10 is followed by 3s. 11, 12 is followed by 3p. 13, 14, 15, 16, 17, 18 is followed by 4s. 19 and 20 is followed by 3d. 1, 2, 3, 4, 5. 21, 22, 23, 24, 25. We've run out of unpaired space, so 26. Whew, that took a minute. And that's the orbital filling diagram for iron. 26 electrons. A lot of full orbitals and a few that aren't. All right. Let's go ahead and do strontium. Strontium is covered up by my workspace, so let's boop. And here it is, strontium, element 38. Now, here's a hint. Strontium is on the 5th row, so that means that it has 38 total electrons. It's on the 5th row, and it's in the S block. Okay, it's in the second column, so this is the S block. Okay? Meaning that I don't have to sort of guess where I'm going to end up. I know that I'm going to finish in 5s. So 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s. Okay, so 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s. Okay, because of where strontium is located in the periodic table, I know that the last electron is going to go here. So 38 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38. And that is the orbital filling diagram for strontium. Okay, so just to be certain, these are orbital filling diagrams. Okay. They are called that because we are actually drawing out the orbitals and then we're filling them in. Okay. As names go, it is fairly on the nose. But as you can see, this takes up a lot of space. So that's why we came up with electron configurations. Electron configurations are a lot more popular. Now, orbital filling diagrams do have their place. Because, for example, we see here, carbon has 2 unpaired electrons in its 2p sublevel. That means something. That is significant. It explains something about the properties of carbon. Likewise, iron has 4 unpaired electrons in its 3d sublevel. And again, this explains a lot about the property of iron. Strontium, no unpaired electrons in any of its sublevels, and that explains a lot about the properties of strontium. But let's move on to electron configurations. Electron configurations take up a lot less space. So, electron configurations. For the electron configuration, instead of drawing every individual electron, we just list the sublevels. Okay? So for example, let's do carbon again. Carbon with its 6 electrons. Once again, this is where that shortcut comes in handy because it's the last electron goes in 2s. It's on the second it's on the second energy level. It's in the p sublevel, and also important, it's in the second column of the p sublevel. Okay. So that's how I know this. Okay. The first level only has the s sublevel, and carbon has 2 electrons in it, so 1s2. Followed by 2s2 because the second energy level starts with the s sublevel, and carbon has 2 electrons in there. Then it's full, so then we go to 2p, and carbon only has 2 electrons in there. So this is the electron configuration for carbon. 1s2, 2s2, 2p2. Those are all 6 electrons for carbon. Let's do something a little bit bigger. Let's do 10. Okay, Sn. It is down here on the periodic table. It is element number 50. It is on the 5th row. It's also in the p block, and it's also in the second column of the p block. Okay, so it is going to stop at 5, 5th energy level. It's going to stop in p because it's in the p sublevel, and then it's going to have 2 electrons in that p sublevel. That saves me from having to count to 50. I mean, I could, okay, 2, 4, 10, 12, 18, 20, 30, 32, 36, 38, 48, 50. You can do that, but it's a lot easier just to say 5th level, P block, second column. We're going to stop when we get to 5p2. Okay, so let's go ahead and do gold. Element 79, down here in the middle of the periodic table. Pretty, pretty shiny gold. All right, gold has a total of 79 electrons, but it's, let's see, 1, 2, 3, 4, 5, 6. It's on the 6th row, which means this is 5d, and it's in the 9th column of the D block. Let's go ahead and close this real quick. So 1, 2, 3, 4, 5, 6, 7, 8. 9th column of the D block. So we're going to stop when we get to 5d9. It's a heck of a lot easier than trying to add up and not lose count and get to 79. So 1s2, 2s2. Remember, I'm able to do this super fast because I've had a lot of practice, but I'm just following along the periodic table. 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, 4f, 5d, and so on. Okay. I recommend you go slow and careful at first. Once you have a lot of practice, you'll be able to do this quick. But 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6s2, 4f14, 5d9. All right, be careful. Be very, very careful about that F subblock. That will screw a lot of you up. A lot of periodic tables don't have this handy purple swatch here to remind you that the F block technically goes in between S and D. But you will have to remember that, otherwise you'll get the heavier elements wrong. But this is the full electron configuration for gold. Oops, there we go. Bring it back up. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6s2, 4f14, 5d9. Now, that is a lot. Okay, 2, 4, 10, 12, 18, 20, 30, 36, 38, 48, 54, 56, 70, 79. Okay, yes. Okay, that's a lot of electrons. We don't care about most of those electrons, which is what's going to get us to the abbreviated electron configuration. However, on top of that, this is also a lie. Well, not really a lie. It's just incorrect. Reason being, look at this. Here we have 6s. Well, let's put that aside. The F block makes things complicated. Let's look at silver. All right, silver is a little bit smaller, only has 47 electrons. So its electron configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d9. All right. This is also a lie, and it's a lie in the same way that gold is and for the same reason that gold is. That's because let's look at this. Here's 5s with its 2 electrons. Here is 4d with 9 electrons. Now, 4d is a little bit higher energy than 5s. Okay, just a little bit. That's a pretty small gap. And what 4d has that 5s doesn't is degeneracy. Okay. These electrons that are pointing up, they all look at each other and they see neighbors that look exactly like themselves, and boy howdy, they are happy about that. Meanwhile, you have these electrons pointing down, they look around and they don't see quite as many neighbors like themselves. They're pretty happy. They've got some degeneracy there, but they could be happier. They could have more degeneracy. So what ends up happening is that this electron jumps out of 5s into 4d. And that gives you, woof, a lot of degeneracy. Okay? So you have to put in a little bit of energy to bump it up from 5s into 4d. But when you do that, then boom, you get so much energy back out from all that degeneracy. It's so much more stable. It's so much happier. So that means that the actual electron configuration for silver is not going to end in 5s2 4d9. Instead, it ends in 5s1 4d10. In other words, there are exceptions on the periodic table. There are exceptions to electron configurations in orbital filling diagrams, and you are going to have to remember these. Okay, it's based on electron degeneracy, and you only have to remember it here in the D block. Okay, it applies to the copper group and to the chromium group. Okay, so bopping back over to the periodic table, you see here chromium is in the 4th column of the D block, so it is one shy of being half full. Likewise, copper, the copper group, that's in the 9th column of the D block, they are 1 electron short of having a completely full D sublevel. Half full and completely full, okay. Okay, so a half full D block or D subshell or a completely full D subshell. Come on, focus, 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 focus. I guess that's the best I can expect. All right, so half full or 100% full, really, really degenerate, really stable, really happy. So that's going to have a lot of impact later on when we start talking about some properties of the different elements based on their electron configurations. But it also has an impact here and now, such that you have to remember the chromium group and the copper group give you exceptions to your electron configurations. Okay. So in order to display that, I will also take advantage of having to teach you abbreviated electron configurations. Okay. So abbreviated electron configuration. We don't actually care about most of the electrons in an atom. Okay. So for example, here is silicon, 1s, 2s, 2p, 3s, 3p. All right, so silicon has 14 electrons, 1, 2, and the 1s, 2s, 2p, 3s, 3p. So 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay. When you look at that, what you can see is that most of these electrons are buried way inside the atom. Remember, this is like actually a three-dimensional sort of spherical structure. So these electrons are on the outside of the atom. These two electrons are buried way the hell on the inside of the atom. Okay? So these electrons can interact with the outside world. These electrons cannot. Okay? So we make a distinction between core electrons and valence electrons. Okay? Valence equals the electrons of the highest energy level. And the valence and the core electrons are everything on the inside. They're everything that's not a valence electron. Okay? It gets a little bit more complicated than that, but that is oops. Okay, still no questions. All right. But that is what it boils down to. Okay. Oops. So, for the abbreviated electron configuration, we abbreviate the core so that we don't have to list all of those electrons. It doesn't make a difference for the smaller atoms, but it does make a big difference for some of the heavier atoms. Okay. So let's take a look at some core versus some valence electrons. And we'll do it with, once again, silicon. Okay. So silicon, with its 14 electrons, here's the full electron configuration. 1s2, 2s2, 2p6, 3s2, 3p2. Okay. So these, in the highest energy level, are our valence electrons. These are our core electrons. Okay. Now here's the thing. 1s2, 2s2, 2p6. Let's go ahead and look at the periodic table. 1s1, 1s2, 2s2, 2p6, that's neon. That is the previous noble gas from silicon. Okay. That is not a coincidence. Okay. The core electrons of any atom are always going to be the electron configuration of the previous noble gas. So that is how we abbreviate our electron configuration, because the core of silicon is equal to neon. So to write the abbreviated electron configuration of silicon, we just take those 10 electrons, we call them neon, and then we write out the valence electrons of silicon like that. Just 3s2, 3p2. Because really, those are the electrons we care about. They're the ones on the outside. They're the ones that are available to do chemistry. Ooh, I've been talking a while. All right. Okay, so let's do something a little bit more significant. Let's look at lead. Plumbum, 82 electrons. If we were to do a full electron configuration, or, God forbid, an orbital filling diagram for lead, that would take forever. Fortunately, we don't have to, because we're doing an abbreviated electron configuration. So the previous noble gas, notice that I said previous, not closest or anything like that. The previous noble gas, we go left from lead, then back up. The previous noble gas is xenon. That's 54 of our electrons right there. Whew, that takes care of a lot. So xenon takes care of our first 54 electrons. That takes care of down to 5p6. So now we just start with the valence, meaning we're going to start with what comes after xenon. What comes after xenon is 6s, then 4f, 5d, then 6p. So those are going to be the not core electrons. So 6s2, 4f14, 5d10, and finally 6p2. And that is the abbreviated electron configuration for lead. Xenon, and then these guys. Now, I want to go ahead and say, these guys don't participate in chemistry. They are very full, okay? They are degenerate as hell. 14 electrons, 10 electrons in those full sublevels. They're kind of honorary core. And this looks kind of like a dude with a mustache. Hello. So they're honorary core. So the ones that actually participate in chemistry for lead are the 6s and the 6p electrons. They don't have any degeneracy to speak of. They actually participate in chemistry. They are definitely valence. The 4f and 5d, we have to include them out here because they're not buried in xenon, but they don't really take place. They don't take part in chemistry. Okay, I just want to stress that because it'll help understand the behavior of some of the heavier elements moving forward. If you remember that these full sublevels, the F and the D sublevels, don't really participate in chemistry, but we have to include them out here because they're not in here. They're not part of the abbreviation, but they still exist, so we have to put them out here. All right, so those are some examples of abbreviated electron configurations. You take the core electrons and you just collapse them as the previous noble gas. Okay. So let's go ahead and let's get fancy. Let's do tungsten, W. You can just barely see it, element 74. Okay, so W, tungsten, element 74, so 74 electrons. The previous noble gas is, once again, it's going to be xenon. So that takes care of 54 electrons. What? Just, oh, okay. All right, so now, once again, we start at 6s2, but we're going to end at, you can't really see it, but 1, 2, 3, it's in the fourth column. So 6s2, 4f14, 5d4. And hopefully that struck kind of a chord with you. It probably didn't, but fourth column of the D block, that's the chromium group. That's one of the exceptions you have to remember. So no, it's 6s1, 5d5. Good thing I'm wearing black shorts. All right. So remember those exceptions, the fourth column and the ninth column in the D block. Those are going to promote an s electron into the D subshell. Technically, the same sort of thing happens down here in the F block, but the F block is evil and mostly doesn't exist. We don't go there. That's the elephant graveyard. Shh. These guys are like all exceptions. They're hideous and hateful. I mean, they might give you one on the test if they're feeling mean, and chemistry teachers especially, often feel mean. But the exceptions that you definitely have to remember, 4 and 9 here in the D block. Chromium group and copper group. Remember those. Remember. Okay, let's hop back over here. Okay. This some practice for you. And now the final thing. The final doohickey to remember. Orbitals have shapes. These shapes influence how they behave when it comes to chemical reactions, because they actually do determine the locations of electrons. The S sublevel is always spherical in shape, and I believe that is where the name of that sublevel comes from, because in German, the word for sphere is Sphäre. So I believe that's where the S comes from. Now, the p orbitals are shaped like peanuts. That's almost certainly not where the p comes from. But they point along each of the 3 axes, x, y, and z. The d orbitals are shaped like clovers, 4-leaf clovers, except for this one here, which is sort of a peanut with a donut in the middle. It's kind of weird, but that's just the way it is. And then you have the F sublevels, which are not nice. They take the cloverleaf thing and they explode it out into 3 dimensions. They will absolutely expect you to be able to draw an S, a P, or a D orbital on the test. Not an F, because the F sublevel is hideously awful, but S, P, and D. And that's easy. S is a sphere. P is a peanut. Just draw the 2 lobes. It's a bow tie, however you want to remember it. D is a clover leaf. Okay. That's it. That's all you have to do to draw an S, a P, or a D orbital. And that is all they would expect you to be able to do. All right. Be able to draw them. They have shapes, and those shapes play a big role. Later on, when we get into how chemical bonds are formed, this will be important. Okay. All right, and with that, we are done with the second set of lectures. I really should have taken a break in the middle. I am dry as can be. I will go ahead and call it a night, though. We will finish. We won't do the worksheet here tonight. I'll save that for class. We will finish Chapter 2 tomorrow when we go over Section 12. We talk about, that was way zoomed in, when we talk about the periodic table. That will be a nice short lecture, but I don't want to do it tonight because, I don't know if you can tell, but my voice is failing me. All right. I will go ahead and I will see you later for Chapter 2, Lecture 12,